is equal, it is Q enclosed divided by epsilon naught. So here it is theta divided by, this is 2 pi, where theta is the plane angle, right? So these are some of the basic formulae which you have to remember to solve the problems based on electric flux and Gauss's law, right? Okay. So now let's see what is the flux due to a point charge. So here we have a point charge. So here we have a point charge. This is a point charge. Now here we have a disk such that the charge lies on the axis of the disk and the semi-vertex angle subtended by the rim of the disk is, suppose it is alpha, right? So this is alpha, and say this is at a distance of x, and say this is radius r here. Okay, so now we have to calculate what is the flux coming through. So we have to calculate here flux coming through the disk. So this is flux coming through the disk, right? Okay. Now, first of all, let's see what is the solid angle subtended by the disk here at the charge whose semi-vertex angle is alpha. So remember here, the solid angle subtended here is sigma, or we can call this, this is omega. Omega is equal to, it is 2 pi, so it is 1 minus cos of alpha, where alpha is the semi-vertex angle, right? Now we have to calculate here the partial flux because the charge produces the electric field in the 3 dimensions, that is in all directions. So some of the electric field lines will pass through this. So you have to find what is the flux through this disk. So the flux through the disk is given by phi disk is equal to, okay, so using this it is Q enclosed, so this Q here is charge, then divided by, it is epsilon naught. Now we have here it is omega divided by 4 pi, right, where 4 pi is the total solid angle subtended. So we can write here it is Q divided by epsilon naught, then it is here omega, this is equal to 2 pi, then it is 1 minus cos of alpha, so divided by 4 pi. This pi and pi cancel, so 2 1s are 2 2s are. We can write simply Q divided by 2 epsilon naught, right? Then it is 1 minus cos of alpha, so it is 1 minus cos alpha. Cos alpha here, this is alpha, so this is base, this is perpendicular, and this is hypotenuse. So this will be equal by Pythagoras theorem, it is x square plus r square. So we can calculate here, it is x then divided by, that is base, divided by, it is hypotenuse. The hypotenuse is here, it is x square then plus r square. So this is the flux through the disk by a point charge on its axis at a distance x. So this is first problem. So this is question number 1, right? Okay. Now we have a similar question here where we can use this type of formula, that is Q divided by epsilon naught. So it is theta divided by 2 pi, right? So I have another question here, that is question number 2. So what is that question? I have here a ring that is uniformly charged, or we can say the charge is uniformly distributed over it. This is a positively charged ring of radius r, right? So I have a positively charged ring. This is uniformly positively charged ring. So here we have center of the ring such that the radius of the ring, it is equal to r, right? Okay. Now I consider here a sphere whose center is on the periphery of the ring and whose radius is exactly equal to the radius of the ring. So I have here, this is a sphere such that the radius of this sphere is r, right? Okay. Now what I have to do, I have to calculate what is the flux through the sphere. Now for that I have to see what is the charge enclosed by the sphere. The charge enclosed by the sphere we can calculate, we can do it directly by this formula. So I can write here first of all, if this is r, this is also r, so this is the periphery of this is the periphery of this. So if I join these two, this is also equal to r, right? Now if I join this point with this point, so this is also equal to r, and if I join this point with this point, this is also equal to r. So this becomes an equilateral triangle. So that means then this angle is equal to 60 degree. So 60 degree, it is pi by 3. So it is pi by 3, right? So the total angle subtended here is, it is 2 pi by 3. So this is also pi by 3. So it is 2 pi by 3. So that means our theta is equal to, it is 2 pi divided by 3, right? Now, if Q is the charge on the ring, right, then we can use directly this formula. So flux through this is pi e partial. So this is 2d equal, it is Q divided by epsilon naught, where Q is the total charge on the ring, and here angle subtended is equal, it is 2 pi by 3. So it is 2 pi by 3 divided by, now here it is 2 pi, so it is 2 pi. So we can calculate here 2 pi and 2 pi cancels. So what we get here, it is Q divided by epsilon naught into 1 by 3, or we can write simply, it is Q divided by, it is 3 epsilon naught. So this is pi partial, so this is 2d, right? So this is another problem here. So we can calculate what is the flux. So this is the case of partial flux, right? Okay. So knowing, remembering these formulae, so we can solve the other these problems also, right? Okay. So now, if we have a dipole, so what will be the flux through a disk at the equatorial plane, right? So we have here a dipole. Suppose this is a dipole. So the dipole has two equal and opposite charges. This is plus Q, and here this is minus Q. So I can name this question number 3. This is question number 3, right? Okay. Now, the dipole moment of this dipole is, it is from negative charge to positive charge. So I can show it like this. The dipole moment is along this direction, and this is here the midpoint. So this will be the equatorial plane. This is equatorial plane. Now here we have a disk, and suppose the radius of the disk, and this is symmetric disk above and below the axes of the dipole, right, such that its radius is, say, r, and say this is L here length, or we can call it as r, or we can call it x, whatever you like. So this is r, this is r also, right? Now since it lies on the equatorial plane, that means it is symmetric with respect to the negative charge and the positive charge. And from the concept of electric field, we know that the electric field intensity on the equatorial line of the dipole is opposite to the dipole moment. So that means the electric field will be along this direction. That is parallel to this axis, but opposite to the dipole moment. So this is electric field, right? Okay. Now we have to calculate what is the flux through this disk by the dipole, right? So if we join these points like this and like this, and suppose this is alpha here, so then this is also alpha, and this is also alpha, right? we have to calculate now what is the electric flux through this. So that means it is simply the electric flux due to this charge and electric flux due to this charge. The field is in this direction, so field is in the same direction. The two fluxes will add up. So I can write here total flux. Total flux is equal to flux due to plus Q, and then it is flux due to minus Q, right? So that is equal to flux due to plus Q. So it is just like we have calculated here the flux due to the one charge. So if it is R, this is R, so this will be under root of R square, then it is plus R square, right? So we can calculate now, it is Q divided by 2 epsilon naught. It is Q divided by 2 epsilon naught, then it is 1 minus, so then it is base, so it is R divided by under root of, it is R square plus, it is R square, right? So then again plus, it is Q divided by 2 epsilon naught, so then it is 1 minus, it is R divided by under root of, so it is R square plus, it is R square. Since these are two similar terms, so it will be 2 times, so 2 and 2 will cancel, we get Q divided by epsilon naught, so it is 1 minus R divided by under root of R square plus it is R square, right? Okay, so now this question can be put in another way, right? If the disk does not lie on the equatorial plane or in the equatorial plane, so then what we have to do? That means this R and R will not be same, so it will be R1 and R2. So if this is R1 and R2, right? So if it is R1 and R2, then what we have to do? So we can solve it again easily. Now this is R1 and this is R2, right? So then this will not be alpha and alpha. So I can call this as alpha 1 and this as alpha 2, right? So what we do here, we can write here then phi is equal, it is phi plus, and then it is plus, it is phi minus Q, right? So this implies phi is equal, now phi plus Q, so again it is Q divided by 2 epsilon naught, right? Okay, now it is 1 minus, now here it is R1, so it will be 1 minus, it is R1 divided by, so it will be R1 square plus R square. It is R1 square plus R square, right? Then plus, again it is Q divided by, it is 2 epsilon naught, so it is 1 minus, it is R2 divided by, it is under root of, it is R2 square, then plus, this is R square. So this way we can calculate the electric flux due to two charges through a plane that is perpendicular to the line joining the two charges, right? Okay. Now, if the two charges are similar now, so this is plus Q and this is also plus Q, so this is plus Q and this is plus Q, then instead of plus here, so we have to write minus, because the electric flux of this charge will be along this direction and electric flux of this charge will be opposite to it. So in that case, so we have for similar charges, so what we do here, that is, it is Q and Q, right? So both are positive, this is positive, this is positive. So in that case, what we do here, phi is equal, it is Q divided by 2 epsilon naught. So then it will be 1 minus R1 divided by under root of R1 square plus R square. Now here, instead of plus, so what we write here, it is minus Q divided by 2 epsilon naught, it is 1 minus, it is R2 divided by, it is R2 square plus then it is R square, right? So this will be the electric flux due to two similar charges placed at one point and this is another point. So we had to calculate what is the flux through this, okay? Now, here another question may be asked like this. So if we have a dipole, right? So what will be the electric flux through the equatorial plane? So when it is asked as what is the electric flux through the equatorial plane of the dipole, so what we have to do in that case? In that case, when we talk of the equatorial plane, so here the dimensions are not given. So when it is given as equatorial plane, so the dimensions are infinite, means we have to calculate the electric flux through the whole equatorial plane. So in that case, what we do, we will just put this R, it is infinite, so it tends to infinity, right? So we have to calculate what is the electric flux, right? So, so from this relation, so we have to calculate what is electric flux through equatorial plane of a dipole, equatorial plane of a dipole, right? We know electric flux due to dipole, so I can write here electric flux due to dipole through a disk is given by, that is equal to Q divided by, it is epsilon naught, then we have 1 minus, it is R divided by under root of, it is R square plus this is R square, okay? So very easy. Now, for equatorial plane, so it is an infinite case for equatorial plane, so what we do here, the dimensions are infinite, means this disk can be made infinite. So when we make it infinite, means R tends to infinity. When R tends to infinity, so as compared to this R, this is very small, right? So this will become infinite. So infinite, anything divided by infinity, so that will be equal to 0. So then we have, it is dipole through equatorial plane is equal, so it is Q divided by epsilon naught. So it is 1 minus, this is R divided by, so it will be R square plus this is infinity square. So it will be infinity, so this is Q divided by epsilon naught. So it is 1 minus, this will be 0. Then what we get, it is Q divided by epsilon naught. So it is multiplied by 1, Q divided by epsilon naught, right? So this is the electric flux through the equatorial plane of the dipole, right? Okay. Now, these are some of the cases for two point charges joined together or making a dipole, right? So we had to find the electric flux through a disk or through a plane on the equatorial axis, right? Okay, so now if we have a point charge, so we have another question here. We have a point charge. This is a point charge. And here we have a disk, right? So this is the axis of the disk, right? Now, this is here semi-vertex angle, and here it is charge Q, right? Now, by Gauss's theorem, the electric flux through any closed surface enclosing this charge Q is Q divided by epsilon naught. Now, if the flux through this disk, whose radius is say R, the flux through disk, this is disk here, so this is equal flux through disk is equal to flux due to the whole charge divided by 4. Then we have to find what is the relation between this radius and say suppose this distance. So I can call this distance as it is x. So what is the relation between them, right? So as it is given, so it is phi disk is equal to phi divided by 4. So we can write here phi, the total flux due to this charge is Q divided by epsilon naught, right? And phi disk is equal by using the solid angle, right? So we can write here it is Q divided by, it is epsilon naught, then it is omega, then divided by, it is 4 pi. So that is equal to Q divided by epsilon naught, then it is 2 pi into 1 minus, it is cos of alpha, then divided by, this is 4 pi. So this pi cancels, this cancels. So what we get, it is Q divided by 2, then it is epsilon naught. So it is 1 minus, now cos of alpha. Cos of alpha is, it is base divided by hypotenuse. So it is x square plus it is r square, right? So it is x square, so this is x divided by x square, then it is plus r square, okay? Now, it is given that this phi disk is equal, it is phi divided by 4, so it is Q divided by 4 epsilon naught, so it is 4 epsilon naught, so this will cancel, so this is 2 here, right? So this implies it is 1 by 2, then it is equal, it is 1 minus, it is x divided by under root of x square, then plus r square, okay? Now, we can shift to this side here, so we can write here it is x divided by under root of x square plus r square. So this is equal to 1 minus 1 by 2, that is 1 by 2, right? So now, squaring both sides, what we get here, okay, so what we get here, this implies it is x square divided by, this is x square plus r square is equal to, now it is 1 by 4, so it is 1 by 4. So what we get here, this implies it is 4x square is equal to x square, then it is plus r square. So this implies 3x square is equal to r square. So we can get here x is equal to r divided by 3. Because we have calculated the distance, so I have taken only one root, that is x is equal to r divided by 3. Okay. So this is how we calculate the relation between x and r when the partial flux through a disk is given in terms of the total flux, right? Okay. So this is one type of problem. So now we can also calculate the flux due to the charge distributions, like we have linear charge distribution. So we have linear charge distribution. So how can we calculate the flux due to the linear charge distribution? So due to the linear charge distribution, we can calculate the flux like this. So I have another question now. This is question number 5, right? Okay. So here I have a semi-infinite linear charge distribution. A semi-infinite linear charge distribution, right? So this is semi-infinite linear charge distribution. So on this semi-infinite linear charge distribution, we have here the endpoint. So now we have to calculate the flux through the disk at this point, right? Suppose this is here linear charge distribution. Suppose the charge per unit length or the linear charge density is lambda. Now we have to calculate what is the flux through this disk whose radius is, say, it is r. This is radius r. So I will show it here. This is radius r, right? So what I have to do here, I have to calculate the flux. So flux we can calculate here. If I take here an annular disk at a distance of y, means a disk element, or you can call it as a ring element, right, such that the thickness of the ring element, this is thickness of the ring element. So I will show it here. This is, say, dy, and say this is y here, so at a distance of y, right? So this is the ring element. So I will first calculate what is the flux through this small ring element. then using the concept of integration, I can calculate what is the flux through the total disk, right? Now, let's see first what is the electric field here. What is the electric field here, right, at a distance of y due to this linear charge distribution. So, if electric field here is E, so this is E, then I can resolve this into two components. One is along this direction and another is along this direction. So this is EX and this is EY. Right? Now this E is given by, E is equal, it is EXI, means along the x-axis, then plus this is EY, then it is J, right? So this is EX, so EX is here equal lambda by 4 pi epsilon naught. This is lambda by 4 pi epsilon naught, then it is Y. So this is I cap, then plus it is lambda by 4 pi epsilon naught, then it is root 2, then it is J cap. Now, since this EY will not contribute to the flux, right, because it is in the plane of the disk, whereas this EX is perpendicular to the plane of the disk, so only this component will contribute to the flux, right? So therefore, what we do here, we can calculate the electric flux first due to this surface element, or we can call this as ring element. The area of this ring element, this is area of the ring element, so I can calculate here, this is dA. So since the thickness of this is dy, so it is circumference is, it is 2 pi y, so I can write here it is 2 pi y, then it is dy, right? And our E here is now equal, that is Ex is equal, it is lambda divided by 4 pi, then it is epsilon naught, it is Y. So Y is here in the denominator, right? Now, what will be the flux? So flux through this ring element, we can calculate here as d phi E. So it is d phi E is equal to, so it is Ex, then it is dA. So this is equal, what is Ex here? Lambda divided by 4 pi epsilon naught, it is Y. Now dy, this is 2 pi, then it is y, so it is dy, right? Now this y and y will cancel, so pi cancels, this is 2 1s are, this is 2 2s are, so it is lambda divided by, it is 2 epsilon naught, right? So what is left here now, it is only dy, okay? So we have calculated now total flux, that is what is the flux from the center to the periphery of the disk, that is of radius r. So our y is varying here from 0 to r, right? So what we do here, then this phi is equal, it is integration of this d phi E, then from 0 to r, right? So it is equal to integration from 0 to r. Now d phi E is lambda divided by 2, this is epsilon naught, then it is dy, so this is equal to lambda divided by 2 epsilon naught, integration from 0 to r dy, so that is simply equal to lambda divided by 2 epsilon naught, so then it is y, for integration from 0 to r, so that is equal to r. So this is flux due to line charge distribution or linear charge distribution of semi-infinite length, or we can say the disk lies at one end of this semi-infinite linear charge distribution, right? Okay. So this is the flux due to a linear charge distribution. But we may have the questions that are of different type. So we have, for example, here a line charge, and in front of the line charge we have a wire frame, that may be a rectangular line wire frame, or that may be a square wire frame. So we have to calculate what is the flux due to this line charge through the wire frame. So we have another question, that is question number 6. So here we have a line charge. So this is a linear charge distribution, right? So it is infinite, extending both sides, right? So suppose the charge density is lambda, and here we have a wire frame, and suppose its length is L and width is B. Okay, and this is like the hand is held in front of the charge, okay, such that the distance between this and this is D. So this is the question. So we have to find what is the flux through this wire frame of length L and breadth B. So length L and width B, right? So what we do here, since this is a line charge, so the electric field lines will be in all directions like this, 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 and this, right? So it is a two-dimensional flux here, okay? So what I do here, I take the line charge here, and I just imagine here a Gaussian surface that is symmetrical with respect to this line charge, and that Gaussian surface is say a cylinder. So this is a Gaussian surface, such that this Gaussian surface contains the wire frame, or it is in the Gaussian surface, right? Now this is here extending, this is here extending, so this is lambda, right? Now the center of the cylinder is here, so this is one side of the wire frame, this is another side of the wire frame, okay? So if I draw here a perpendicular, so I draw here a perpendicular, this is the top view, so this is top view here. So what actually we have to do, we have to calculate the electric flux through this wire frame, okay? And remember, these two lines, these are of equal length. So if you look from the top, so from the top view, so if we take the top view, this is top view. To make it easy, let's take the top view. So this is the top view of the wire. So it appears as a point, okay? And this is one end, this is another end. Okay, so just like this. So now, so the length of this side will be B. So if we draw here a perpendicular, so that we can take this angle as theta, this angle also as theta, so this will be B by 2, this is B by 2. And this distance here is, it is D. Now let's first see what is the charge enclosed in this Gaussian surface, right? So the charge enclosed is, the length is L, so the linear charge density is lambda. So charge enclosed is equal, so I can call it as Q enclosed, that is equal, okay? Now linear charge density is lambda and length is, it is L, so it is lambda L, right? Okay, now using the formula for partial flux, two-dimensional partial flux, right? So flux through this is equal, it is phi is equal, it will be Q enclosed divided by, it is epsilon naught then it is theta. So theta is this divided by, it is 2 pi. Okay, so we can write here Q enclosed, it is lambda L divided by, it is epsilon naught. Now theta here is, so we don't have theta given here, so we have only these two sides, this is perpendicular and this is base. So tan theta is equal, it is base by hypotenuse, so it is tan theta is perpendicular divided by base, so that is b divided by 2 divided by d, right? So this implies theta is equal to tan inverse, this is tan inverse, it is b by 2 then divided by d. Okay, so now for theta we can write here tan inverse, this is tan inverse, then it is b by 2, then divided by d, then divided by, it is 2 pi. So this is the flux due to the linear charge distribution through a wire frame. Okay, so this question can be again modified, so we can shift the line a little bit up, right, and we can make another question through this. Okay, now this is the partial flux due to the linear charge distribution through a wire frame. Now similarly we can have another question like this. We have a hemispherical bowl. This is hemispherical bowl, say of a radius r. So this way it is also r, right? It may not be symmetric, right? So but you just imagine it is a hemisphere. Okay, now a charge is placed here, a charge is placed here, this is charge q, such that this distance delta r tends to 0. When the question is given like this, so it is delta r tending to 0, right? So it means the charge is very close to the center of the base of the hemisphere. So we can directly calculate what is the flux. The flux here is, since the charge is here, so we need two hemispheres. That is, one is this hemisphere and another another part of this. So that means the full sphere. So total flux will be through the full sphere, that is Q divided by epsilon naught. So then flux through this is phi is equal, it is Q divided by, it is 2 epsilon naught, right? But you can also do it like this. You can imagine this as a disk here. So you have to find the flux through this disk, right? So if this is the angle alpha, that is semi-vertex angle alpha, as we did it with the help of solid angle. So with the help of solid angle, we can also do it with the help of solid angle, right? With the help of solid angle. So what we do here, we can write here, it is phi is equal, it is Q divided by epsilon naught, then it is omega divided by 4 pi. So it is equal to Q divided by epsilon naught omega. So omega is it is 2 pi into 1 minus cos of alpha, then divided by, it is 4, then it is pi, right? Now since it is very close to this center of the base of the hemisphere, okay, so when this tends to 0, so this alpha will tend to 90 degrees. So we can write here, when delta r tends to 0, it tends to 0, then this alpha tends to 90 degree. So in the limiting case, we can write here phi is equal, it is Q divided by epsilon naught, then it is 2 pi, so it is 1 minus, it is cos of alpha is 90 degree, so it is cos of 90 degree, then divided by, it is 4 pi here. So cos 90 is 0, so we can write here it is